Small but mighty.
Out of curiosity, Orlando, why don't you use the setting to turn off OBS streaming itself?
Sorry?
Why don't you have OBS not streaming itself? Because I notice every time you open OBS, it streams itself.
Oh, that's an option?
Yeah.
Oh, I didn't know. Where? I'm going to learn something.
Do you mind?
No, not at all. Please.
It should be. If I go into, I'm just gonna use mouse.
Yeah, go nuts. I had no idea that was an option. That makes a lot of sense as a feature.
I just need to find where it is.
Now, I haven't updated like in a couple of versions.
Shouldn't need to.
Okay.
I just need to remember where it is because I don't remember where it is off the top of my head.
That is so cool that that's an option. I mean, it makes a lot of sense.
It should be
under video.
In. No, it should be in general. I just am very blind.
Automatically recording.
No, it's very obvious that it is what it is.
Well, we'll figure it out tomorrow. But thank you for letting me know that exists. I will Google it. Yeah, that would be much nicer because it does. It does always annoy me on my streams when like it start. The first thing you see is me and OBS. It feels amateurish. Yeah. And when I've got the multiple monitors set up, sometimes I'll even like open up PowerPoint and like make myself a title page, and then I feel fancy. But you know.
I'll figure out what it is when I get home. But
oh, thank you. That I would really appreciate that. That would be that little touch of class I've been waiting for. That and not asking my class, hey, have I told you guys about the Steve Philo share? You know, touches of class. So today we're just going to talk about different ways that we can represent changes in enthalpy. So the first way that we can show enthalpy changes is we can include enthalpy in a thermochemical equation. We can just write the energy into the equation as another reactant or product. Does that make sense? By the way, when do we think of energy as a reactant? What kind of reaction would we say energy is one of the reactants?
No, endothermic.
Endothermic, because energy has to go in. And obviously we would think of energy as one of the products in an exothermic reaction. Very good. So let's look at a couple examples of that. The molar enthalpy of burning ethanol is negative 726 kilojoules per mole, an exothermic reaction. So let's write a balanced thermochemical equation. And you have to be careful here because note it's per mole. So let's write an equation. What is the burning of ethanol? What's the formula of ethanol? Let's all draw ethanol. What would it look like? Yeah, okay. So there we go. That's what ethanol looks like. Hey, what's the hybridization state of this carbon? What are the bond angles here? Could we draw an energy? How many lone pairs of electrons must this oxygen have, even though I haven't drawn them? Very good. If we drew an energy level for it, it would have a full 1s orbital. And then what would its second shell look like?
Two SPs and then 4 spaces.
Okay. And what would they look like?
Oh, 2s3.
Okay. And what would these look like? Yeah, what are those?
Your lone pairs.
Your lone pairs? Very good. All right, that had nothing to do with today's lesson, but good job. We're going to do that from time to time to make sure that stays fresh in your mind. By the way, would this be called ethanol? No. Why not? Because it doesn't matter which carbon you put it on, that's going to be carbon 1. There's no middle carbon for it to be on. Good. Okay. So if we burn ethanol, what is that? 2 carbons, 1, 2, 3, 4, 5, 6 hydrogens, and 1 oxygen. Though usually we will actually, so it would be perfectly right to name it like that. But do you know how we would normally write it instead? Is like that. Both are correct. Why is this a better way to do its formula?
Because there's not 6 hydrogens on the carbon. There's a hydrogen in an O bond.
Yeah, and that's okay. Like, again, these are both correct, but this one tells you that it's an alcohol, whereas this one you would be left guessing. So this is a better formula. What does it mean to burn something?
Heat. Kill it.
Incorrect. By the way, is this a solid, a liquid, or a gas, assuming we're at room temperature? Okay. What are we reacting it with if we're burning it? Very good. What are we going to produce?
Carbon dioxide and water, but sometimes combustion.
And we're going to assume complete combustion, though you're completely right.
Then it would just be carbon dioxide. Carbon.
Okay, and balance this guy out. How many do we, what do we need?
No monoxide.
Sorry?
Isn't your heat reactant?
Yeah, we'll get there. And how much heat?
700 negative. Wait, what? I'm not reading this.
And it's exothermic. So which side's the heat on?
Exothermic means it's on
It's a product. It's being released. How much heat?
726 kilojoules per mole.
Great. And I'm not putting per mole because, again, in a balanced equation, the mole numbers go here, right? And right now, how many moles of this do I have? 1. Well, but right now, how many do I have? 1. So now let's balance it.
So start with 2 on the first.
2 here, okay.
What?
And I think a 5 on H2O. I'm getting it wrong.
Well, let's take a look. 2 times 5 is 10. 2 times 2 is 2 more. So we have 12 hydrogens
Oh,
here.
see the hydrogens, sorry.
That's okay. So how many here?
6.
Yep.
You shouldn't start with a 2.
I've been doing it this entire
He's got it. Settle down. And then how many of these will we need?
Okay, hold on. I'm crossing out of my mind.
Just look at your carbons. Don't worry about oxygens. Look at your carbons.
Oh, we just need 2 CO2.
Look carefully.
Oh, sorry, 4.
Very good. Now, your instinct would probably not to be to start putting a 2 there, but Chris had been jumping ahead, and he knows that we're going to need that 2 there to avoid this being a fraction. And he didn't want a fraction there. And I agree with that. That's cool. So, let's count oxygens now. How many do we have here? Here?
8.
And here?
12, 7. No, 6.
And 6.
Great, for a total of?
14.
Great. Now, keep in mind, how many do we have here? So how many more do we need here? And what number goes in front to give us 12 there?
6.
Okay, very good. If you hadn't doubled everything, this would have been 3/2, 3 halves, which would have been fine, by the way, because the one place we allow fractional balancing is with, yeah, your diatomic elements, just for convenience sake. But I like this better, but keep in mind, now, if there's a 2 here, is this balanced? See, this is kilojoules per mole of,
Yeah, so you need to do 2 7.
so I need to do 2 of those, which means, let's rewrite this. So just keep in mind that when you're making,
Why do you need to do 2? Oh, because it's per mole.
because it's per
of
mole.
ethanol.
Very good, exactly. So just keep in mind that if you are doing a balanced chemical equation, a balanced thermochemical equation, like we just did, you can very much do that. By the way, what is that doubled?
1452.
Very good. It's important that when you balance, you also balance the heat. Very key. Can't ignore that step. You have to balance the heat. Because the heat, as it's given to you here, is expressed per mole.
But it's a negative.
It's joules per mole.
Now, are we ever going to put it in here as a negative? Look here. Look here. It's given to us here as a negative, but I put it in here positive. Why? This negative we are going to use just to tell us which side of the equation it should be on. We are never going to put negative heat into an equation because that's kind of a weird thing to conceptualize. So it's very easy to conceptualize positive energy, right? So we are going to use the sign only to tell us whether it belongs as a product, this would be product for you, or a reactant.
So is this a balanced thermal?
This is now a balanced. thermochemical equation.
That was pretty easy. Like, it's
Not
like
too
the
bad.
same
Now,
way.
having said that, this is probably the least common.
As soon as you said it's easy, this is probably.
Well, because the other ones, we don't do this all that often.
I thought we were just
Right,
doing it as a
here.
go back to grade 11.
You totally can. You can include the energy right in the equation like that. Nothing wrong with that. But more often, what you'll see is that they balance the equation, and then next to it, they write the delta H. That is the more common way it is done. So let's demonstrate that. Oh, sorry, take your time. I'm not trying to rush you. Ah! Ooh, I'm bad at whistling to begin with, but in a mask, much more tricky. Oh yeah, that is, I've never tried to whistle in a mask before.
Is that weird?
Yeah, it's weird. You'd think it wouldn't be, but that, feels strange.
Your airflow is restricted. So.
Yeah, and again, I'm not good at whistling without a mask. Okay, let's look at this one. The second way we show an enthalpy change, and this is by far the most common way, is we will write the balanced chemical equation, and then we will put the delta H on the right side of the equation by writing delta H equals and putting it there. Sulfur dioxide and oxygen react to form sulfur trioxide. Somebody give me this equation. What am I writing? Let's find out. What's the equation?
Sulfur trioxide.
Yep.
S. And then 3 bonded ozone.
Let's just give the equation. Just the equation. Start with SO3.
No.
Okay, well, I'm just doing what you told me to do, team.
Sulfur dioxide is SO2
Okay.
plus oxygen gas.
Okay.
Make sure you put your G.
Do not say equals because it's not an equals. Yeah, and I didn't mention it, but this is a gas, in fact, and this is also a gas. Very good. And what is it going to yield?
Reacts to form SO2.
Very good. And that, in fact, is also a gas. So, and that's balanced and we're good to go.
Nope.
No.
Pretty sure it is.
There's no oxygen there.
There's an extra option.
Aha.
How it's being.
So you have two options here. You could do this, and that is sometimes considered acceptable. So I'm going to start by doing that.
Sometimes.
Well,
Not.
okay.
What makes it unacceptable?
I don't love it.
What? I know you don't love it. But
So there we go. And in that case, when we go to make this a thermochemical reaction, we can just go on the side, and we simply say on the right of the equation, delta H equals, and what is the delta H of this reaction?
98.
Almost.
It's negative.
Very good. And because here it's not on one side or the other, we've simply written it next to the equation, we have to make sure we make it clear whether that is exothermic or endothermic. So we have to include that negative sign. And in this case, we go like that.
Can I balance this?
And sorry, they don't list it per mole, they just list it as kilojoules. This reaction, as it happens, releases 98.9 kilojoules. Because I want to say, if we wanted no fraction, that's no problem. Can we do that?
Yeah.
What would my reaction be if I wrote it balanced without fractions? Yeah, Jonesy.
2 SO2s
Okay, 2 SO2 in its gaseous state.
plus O2
Yep,
and state.
yep.
And it reacts to form 2 SO3s.
Okay. Keep her going. Thermochemical equation. Thermochemical. So what do we need to include in the reaction?
Your delta H.
The delta H. Is the delta H still negative 98.9?
No, it's stuff.
Which makes it? And in fact,
Wait, doesn't it need to be some sort of? Oh yeah, I guess. Wait, does this reaction even happen? How can it be?
Oh, that should be an 8,
grams,
shouldn't it?
grams?
Yeah, it should be 0.8.
sorry.
So yeah, name is Fernando?
Yep.
Oh, gas.
Yeah. So there we go. So just keep in mind that this is by far the most common way you will see the thermal information about a thermochemical equation given to you. The most common way you'll see it is like this. They write the equation, they balance the equation, and on the side they shoot in a delta H. Great, nothing wrong with that. I think this is easier to work with than the one above. Your mileage may vary. I like it because you know where to look. You want to know the enthalpy, you just look on the right-hand side. Every table you look at, you're going to see it like this. But, look at me. Don't forget that if you modify the equation, say you double the recipe, say you triple the recipe, say you make it 10 times bigger, if you modify the equation, you also have to modify the delta H. All right? And we're not expressing it as kilojoules per mole. Rather, what we're saying is this reaction, as shown here, will release that much energy, which means when we change the reaction, we also have to change the energy. Is that reasonably comfortable? We feel okay with that? Okay.
Not really comfortable.
Another way we can do this is diagrammatically. Oh, I'm sorry. Take your time.
Because I
Pencil
watch.
for your hand.
How's Steve the Vendetta doing today?
Have you ever turned it on yet?
Yeah, that's on all the time. I just don't put it on high power mode because that's really loud. Yeah, I find that very unpleasant.
And why are they giving you air purifiers?
Because we're living in a global pandemic with an airborne illness.
And we didn't think of this sooner?
Oh no, they did. They just didn't get them.
You raise a very good point. I will send a letter to my MP. I'll say, dear Member of Parliament. I suppose I should send it to my MPP. Dear Member of Provincial Parliament. Thank you so kindly for Steve for Vendetta. Open bracket, my air purifier, close bracket.
The funny thing is, his name's Austin. It's not even
Stone Cold Steve Austin. There's a method to my madness here.
I thought you just randomly
Stone Cold
Steve.
Steve Austin.
No,
Steven.
No. That's not where he got
No,
it.
I asked the class. Somebody said Steven. I liked it because it was Steve Austin. Is that what you're thinking too, by the way?
No.
Oh, no?
I have no idea who that is.
He's a wrestler from like the 90s.
You know, he like smashes beers and like shoots people from a milk truck.
That explains like half of America.
He's the Texas rattlesnake.
Moving on. Anyway, so Steve for, and if you actually look at Steve for Steve Vendetta, which I really like, but anyway. He's my air purifier, and I love him. Okay. We can also show this as an energy level diagram, which may seem silly, but it's actually good. You know, those math teachers, they're on to something. This idea of showing things in multiple ways of representing the same information can be a really valuable thing. In this case, a graph. So if this is a graph and we're showing how the energy changes, this is basically time. I mean, more accurately, they just say the extent of the reaction, so they don't have to care how fast or how slow the reaction happens. As the reaction progresses, the amount of energy, well, in this case, what is happening? What kind of reaction is this?
I hate when you
What do you
repeat
think?
really racist.
Well, it's losing.
Yeah. So if we look, the amount of enthalpy in the reactants is more than the amount of enthalpy in the. So enthalpy decreases in this case.
Are you gonna erase this?
I might. What would happen to the surrounding temperature?
I don't want to write it. Let me erase it. 'Cause I wrote down.
It's going to increase. If enthalpy decreases, why would the temperature go up?
Because that's the enthalpy of the product, not the surrounding air.
Good. In fact, if the amount of energy inside the chemicals is going down, energy can't be destroyed. So where does that energy go? To the surroundings. So the surrounding temperature will go up. And we would call this what kind of reaction? And I'll actually put that up here as a title. They didn't label the y-axis of this graph. If you were to label the y-axis of this graph, what would you put on it? Very good. Enthalpy. Now, on this graph, where is the delta H?
That's been stuck in my head.
Oh, hello. Oh, no. Okay.
Just opens up Markbook.
No, thank you. That is the delta H. That is the change in energy. And in this case, note what is happening to delta H in this case. Delta H is negative, i.e., this is going down on the graph, not up. I think that can be a helpful way to look at this, personally. Again, your mileage may vary.
No.
How would you describe the graph on the right to me? Good, and can you tell me what that means? You're completely correct, of course.
It means the product has a higher heat than the reaction, so that it has to be.
Good, give me even a little more. What's it mean to say that the product has higher heat than the...
That means the heat goes inside of the products and not.
What's it doing in there?
It means it's moving faster.
Is it just me being crazy, or can all I hear is the hiss from your stereo? Do you hear like the silent
Just
hiss?
you.
The electrons in the compound.
Do you
are
hear
moving
it, or
faster
am I going
and they're more
insane?
energized.
Oh, no,
They're creating bombs.
I gave you your answer.
I do have it down pretty high. I'll put it down. Okay. Shh. What's in your head?
You don't want to.
You don't want to know.
Okay.
Something's in the way by Nirvana, but a different wording of it.
Sounds very mature. Moving on.
It's really not.
So if enthalpy increases, I got distracted by Chris mentioning the hiss, but somebody said that that energy is going into bonds. It's going into forming the bonds that hold that together. And it takes energy to hold atoms together. So in this case, there is more energy holding this product together than there was energy holding the reactions together. By the way, can we measure the enthalpy, the actual enthalpy of the reactions or the actual enthalpy of the
Not
products?
very accurately.
No.
No, but we can measure the change between them. Well, because we would have to measure all of the energy in a molecule, and there's a lot of different sources of energy.
You can do anything as long as.
In this case, what do we know about delta H?
What?
Delta H in this case is
I don't get it all.
positive. And what would happen to the surrounding temperature here, all things being equal? Very good. What term do we use for a reaction of this nature? We would say this is an endothermic reaction. Very good. Yeah.
So, like, the relationship between enthalpy and the temperature of the surroundings, would that be considered a ratio? Sort of?
Yeah. In fact, there's two ways to think of it. We said that Q and enthalpy are equal in magnitude, but opposite in direction, or opposite in direction is the term, actually. Think of these as vectors. But if you want to think of it as a ratio, yeah, we can also say that the ratio of Q to delta H is a constant, but not only is it a constant, it's specifically, we would assume to be -1. And in fact, it would probably be some constant K, which would represent inefficiency. In other words, inefficiency. This would represent heat lost to things other than temperature. Was light emitted? Was sound made? Was movement? No, but it's similar in concept. The idea of a constant. Did that answer your question at all?
No.
Hey, look at that. It wasn't your question, Valut.
I thought that was on the note. Oh, I actually wrote that down.
Well, that's okay. It doesn't hurt. It never hurts to know that. It never hurts to know that we are often going to assume, you can write this if you want, this is a very common assumption in thermochemistry. Can somebody tell me in words what this equation is assuming? This equation tells us what?
Did you not just write it in words?
Well, we're going to use both. Somebody described me. This says Q equals the negative of delta H, and we had a whole talk and said they're equal in magnitude but opposite in direction. They form a constant ratio. Great. What's that mean in terms of actually doing chemistry? What do I mean by that equation?
What? I forget what Q.
Sorry? Oh, I've said this a bunch, and we'll say this a bunch in the future. But it's weird learning to think that a mathematical equation also has like a physical meaning. What's the physical meaning of this? This equation tells me something about the reaction I just did on the bench. What does this equation tell me about the reaction I just did on the bench? Something is the same as something. True.
The energy required to make the temperature change is the opposite of the enthalpy.
Cool. Don't focus on the opposite part, though that's true. Though that makes sense, because really what we're saying is, why are they opposite? What's the physical meaning of that? What's it physically mean that one of these is positive while the other is
One says
negative?
how much energy it takes to change, and the other says something.
Sure, yeah, that's fine. Break it down more. One of these is positive, the other one's negative. What's that mean about the reaction? One thing's positive, another thing's negative. Give it to me.
Moving from one to the other.
Transfer. Do you have an answer for me? Okay, what is it? Then be quiet. Okay, so let's go with yes. So what's it mean? This is key, a key concept. So, because you should definitely be able to describe this, that's important. If this is going up, what is Q?
I forgot.
That's Q. What's Q?
A letter?
Not specific capacity, that's C, but it's related to that. Q is heat energy, thermal energy, temperature. If the temperature in the environment is going up, this is going down. Temperature goes up when in a reaction, enthalpy goes down. When chemical bonds are losing energy, that energy has to go somewhere. Where does it go? To the surroundings. But also, the fact that this doesn't say proportional, the fact that this says equal and exact means that we are assuming that all of the energy lost by those bonds is ending up where? In the environment as heat. That's what this equation assumes. Now, again, is that equation true in the real world? No, it's an ideal circumstance. In practice, other things will happen. But the assumption here is that all of the energy lost in an exothermic reaction becomes heat in the surroundings and temperature goes up. Wherever you want, or don't. And what would the corollary of that be? Have you learned about corollaries in math class? What do we teach you, children? Corollaries mean the implied opposite. So if all of the energy lost in an exothermic reaction becomes heat in the surroundings, the corollary to that is that all of the energy gained in a, or absorbed by, all of the energy absorbed by, and what do we call a reaction that absorbs energy? Very good. All of the energy absorbed by an endothermic reaction comes from heat energy in the surroundings. Now, again, is that always true? No, but these are the assumptions we make when we write these equations.
How would you notate the inefficiency, like energy loss?
You would have a constant here. And if it was 0.85, it would mean you got 85% of that energy, but 15% of it did something else. Great question. Does that make sense?
Yeah.
You'd simply have a slope there. And in practical terms, in a universe where energy can't be created, you would have some constant k here, where such that k is less than or equal to 1.0. Does that make sense? You would say there's some constant there, and that constant can't be better than 1. It can't make energy appear out of nowhere, but it can be 0.6, which would mean energy is doing something else. It's becoming sound. It's becoming light. Yeah. But we're going to assume for the time being that we can just make this a linear relationship. Though that's a wonderful question, because if you do more advanced calorimetry, you measure the constant value of your calorimeter. You learn how inefficient your calorimeter is, and you bake that into every equation. And a calorimeter that you bought, like a professional one, would tell you what its tolerances are. It would tell you how much energy it itself is absorbing. You should say surroundings. Plural. And if it feels like we're belaboring this point a lot, like I kind of thought twice about doing a whole note about this rather than just introducing it to you kind of as we went, but I think it's actually beneficial, A, to give you a day to kind of rest and just take something relatively straightforward in. I think that's beneficial. It's a big concept. It's an important one. Not challenging, but important. A very important concept. You are smart. It is hard. Are you kidding me? We're discussing thermochemistry. We're talking about the very foundations of how the universe around us works. You can feel smart. It's okay. Have a little bit of ego. The world will eventually come around and knock it out of you, but for the time being, enjoy it. Okay, let's try. The gap between two energy levels in a graph of this nature represents the change in enthalpy. So what I want you to do is show me an energy level diagram of the reaction of magnesium and oxygen with delta H of negative 601.6 kilojoules per mole, and another for the hydrolysis of water with a delta H of 285.5. And note, here I wrote reactants because I don't know the reactants. And I wrote the word products because I don't know. But if I did know the reactants, what would I write up here? The actual reactants. And what would I write down here? Very good. So I'd like you to do these energy level diagrams again, but this time actually showing the reactants and the products. Sorry. That was quite a sentence I just spit out.
Why are you abusing your papers?
Paper deserves to be abused.
Yeah, you get better control of your paper.
Cancer.
Get to work.
Man's more deaf than somebody without ears.
Do you have the trick where we can just
Preston, I'm going to advise you to stop that right now. Thank you.
What were you doing, Preston?
Tapping the top of the second page.
Oh my god.
Sorry, I did this while you were speaking, so I'm kind of done.
Can I take a look? Yeah, the only thing is, show both products up here.
Oh yeah, I just forgot to write
But
that.
no,
down.
other than
Sorry, I
that,
ended up
that
writing
looks
formula in there.
lovely. Well done. Very good.
stopping recording?
It just slipped my mind for a second.
No, I'm trying to find that setting.
Oh, in OBS?
Yeah. I'll find it. You do that. I'll find it here. I'm tough. Capture cursor.
Yeah, just because I use OBS as well, and I use that setting.
Make OBS invisible to itself. There's a sentence that doesn't make any sense. Settings, general, hide OBS window from capture screen. Settings, general,
I made it better.
file, settings,
You may have to update it if
general.
it's not there.
That doesn't look sexy.
You need to update.
Oh, you know what? It probably can't do it while streaming. Is that possible?
No, you can do it while streaming.
Oh, really?
I've
You
changed
can
it
change it
while
midstream.
The only settings you can't change during a streaming session is things like your video settings.
Right, which makes
Things
sense.
that change the quality of your
Right,
video.
which makes sense. Yeah, so maybe I just need to run an update.
Because like I can change my bitrate midstream.
Oh, can you really?
Yes.
Oh, I did not know that. That's cool.
But I can't change what my, for instance, I can't change my resolution.
Resolution, yeah.
I had no idea you changed the bitrate while streaming.
Yep. I guess it makes sense because you can run a variable bitrate, right? So why couldn't you just change the fixed bitrate?
Well, let me.
You know what drives me crazy is that you can run like 17,000 kbps in video, but YouTube caps you at 160 kbps of audio bitrate. It's just like, why? Why does the audio on
YouTube,
this have
that's
to be
why.
trash? But like, you obviously have the bandwidth. You're running. You allow. I think they cap out at like 100-some thousand kbps for video. Like you can go crazy, but 160 for audio, which is why like no matter what you do, a YouTube audio stream is just never nice.
That's why I
Can't
get
do
like the best mic in the world.
But it doesn't matter. That's the point. It's just the audio. The actual audio you're sending is so low bit.
Yes.
Like a half decent MP3 would be say 320 kbps, and that's even not great. Sorry? Oh, tons. This is all we're doing. We're just running 2 graphs. Jonesy, you want to come draw one of these?
Another one?
Well, like on my screen.
Yes, another one.
Wondershun. There you go.
Show. Show
Of course means Wondershun.
Wonderson means Wonderson.
Oh, you already did lovely graphs. Please tell
Okay.
me this. If I rotate the screen, it's not gonna rotate on the screen.
No, you're fine. Just leave it sitting.
Oh, perfect.
Are you a responsible educator? Did I get you again?
Yes, you got me.
Why does he keep asking you that?
Because I always say I'm a responsible educator when I do my attendance.
I'll be right back.
I always say,
yeah.
and why am I doing my attendance? Because I'm a responsible educator. The only thing is
You're
I'm not a responsible educator.
And he
Oh,
hasn't done his attendance.
I'm so ashamed.
You heard to do your attendance again.
I did. In my defense, it was a really chaotic start. There is some. It was a chaotic start. The photocopier was slow, and then the math student.
Would you
Biology
prefer
without math.
this or this as the title of the graph?
Blame
Just that, because you'll have these written
In
there.
the-
and
yeah.
that. So you're good. And you don't have to write the word reactants and products. By
Yeah,
the way,
okay.
That's implied. You can. It's not wrong. Braden, how was that? You cool? You got it? You got it done? Today's word. Straightforward? You know what you're doing?
Yeah, it's okay. It's tedious and annoying.
It is too. Do you want? Do you need help with it? Or are you good?
No, it's just messing a bunch of stuff around.
Basically.
Bunch of-
I appreciate the change. Well done. Well played. You can zoom in if you want. If that'll help you be neater.
Oh, thank goodness. Where's the eraser?
You don't have to. You can just use the back. Use the back.
Oh,
Use the
wait.
back.
It doesn't erase.
Yes,
Oh,
it
thank
does. Be patient.
My line's gone.
Back. Back.
Patience was never an option.
Will, can you come massage me?
What are we doing?
I don't.
I mean, okay. The what we're doing was rhetorical because I obviously have eyes and knew what you were doing. I guess what I meant to say was. I guess what I meant to say was settle down.
That's
Yeah, go nuts.
That's like the creepy teacher just coming up behind you.
Oh God. Ugh.
Massaging your shoulder.
Oh no.
So, how are you doing?
Okay, sit down.
I feel like I've had that type of teacher and I've
Oh,
just
God.
given the worst glare that I've ever given to them.
Yeah, let's keep the.
Yeah, that fun.
There we go. Oh, wait, I forgot to
Record
guess.
that.
Record what?
Our
Here you go,
teacher
Orlando.
stuff.
It's kind of messy because I don't use the tablet, but
No,
it's
I did
there.
not.
Now go do your attendance.
Okay, that looks great. The only thing I'm going to bounce back on, like, it's very, very good. And I love that you showed it curved because, of course, things happen like that over
Where are
time.
you going?
You wanted me to put the H there, didn't you?
Yeah, that's okay. What is the delta H in this case?
It is negative 601.1 kilojoules per mole.
Very good. And let's look carefully here, guys, because I will say the other thing I'm going to bounce back on here
How do you balance it with that? No, it's
Boing, boing.
balanced.
is there such thing as MG2?
It's
Sorry,
not.
I didn't catch that. Where should the 2 be? Yes, we need 2 of them.
4.
Got to be in front. Now listen. Shh. Hey, look here. Key concept.
What's the LOX concept?
Which is if we have 2 moles of magnesium, what's that delta H?
How does that shape you slide?
Double
Yeah, which would be what?
1202.12.
Oh, I love that riff. It's so good. But that's great. Well done. And the next reaction should look something like this. Now, how would I express this delta H?
With your words.
Positive.
Okay, it's positive. I like that. What else can you tell me? Good. So it would be what?
400. No, 500. Can I do that in my head? No, I can't.
Yes, you can. 80 doubled would be 60. 5 doubled is 10, so that's 70. So 571.0.
Stop flexing on us, Orlando.
You know what the trick to mental math is?
Knowing math.
No, practice. And you know what the trick was? I used to work at a fish market, and it was crazy busy. And the lineup for the till, there was like 5 of us employees, and the till was always kind of super slow going. So I always tried to know the number in my head before I would get there. And then that was back when people used to pay cash for just about everything. So I would always have them give me the cash, and so I could get to the till and pull the change out as I was scanning the stuff. And so I got very, very good at kind of multiplying numbers and adding and subtracting, because like the scale would tell you that you had like
Fish.
yeah, the scale would tell you that you had like, 2 pounds 4 ounces of fish, and so in your head you knew the price per ounce, and you just have it worked out with tax and with change and everything by the time you got there. So I got pretty good with it. I'm out of practice now.
You need to go back to the fish.
I worked there for 11 years.
11 years?
11 years at one restaurant. And I did literally every job in that restaurant except owning it. I was, because it had a market too. So I worked in the market. I was a bus kid, a dishwasher, a host, a bartender, a server, head server. I worked in the kitchen. For one very unfortunate month, I ran the kitchen. Let me tell you, yeesh. I was a prep cook, and then eventually I was a manager. And it was a great job. I really loved it.
Were you one of the fish, though?
I once had to dress up in a large lobster costume. That's a true story. That's a true. I wonder if I have a photo. I will check at home to see if I have a photo of me in the large
I'm gonna
lobster
be
costume.
honest with you, that was
Well, we
not
had
the
a
answer
mascot.
I was expecting.
We had a mascot, and during lobster season, we would pay this person to go stand out on the road, and I lost a bet, so I had to do a shift in the lobster costume.
I am glad I asked that question.
And
but
I'll
that
tell
is
you, it
not
was
the answer
stinking
I
hot.
expected.
You need to go back and work as owner.
The place is closed now.
No, just
so
work as a
that ship has
lobster again.
sailed.
Mr. Orlando.
Yeah.
So when we're doubling or tripling or quadrupling the age, we're only like looking at the reactants. If the reactants are double, then you double, or is it?
As a rule, when it tells you kilojoules per mole, it's talking about, you have to be careful, But in most cases, it's talking about the primary reactant. So in this case, magnesium, or in this case, water.
What?
That's Spanish. Yo. Oh no, just yo, bro.
Okay, there's no homework today,
Look at.
which is good. Tomorrow is a very key concept. Make sure you have done the previous homework in this unit coming into tomorrow, all right? It's going to ramp up in intensity a bit, this unit, all right? It covers a lot of big concepts, and you need to be comfortable doing that little bit of stoichiometry. I am attempting to get my grade 12 practice app running with some stoichiometry of thermochemistry equations. I've been running into some, let's say, obstacles. I'm facing challenges.
Didn't you just have
The
like a normal
difficult-
stoichiometry one last year?
Yeah.
I am
She
quite
did struggle to make.
well, but
say the
works. It's perfectly cromulent.
Really? Perfect.
But
How's the
do you know that joke?
grade 11 one? We're gonna.
Grade 11 one I'm pretty happy with. Perfectly cromulent word is one of my favorite jokes in the Simpsons, which is the motto of Springfield, the town, is a noble spirit embiggens the smallest man. The joke, of course, being that the town is so stupid that embiggens isn't a real word, but it's in the town motto. And there's a scene once where there's just two people talking in front of the statue that has that on it. And the guy says, you know, I'd never heard that word embiggens until I moved to Springfield. And then the other guy says, I don't know why. It's a perfectly cromulent word. Anyway. I happen to think that's the structure of a literally perfect joke.
I don't
No,
know
it's
about that one.
it's very much so not literal.